All right, I think it's time to get started. Welcome back to everybody. We are talking about integration by parts. No quiz today. Sorry about that. We'll make it without the quiz. Integration by parts, you got to remember the formula. Integral u dv equals uv minus integral of v du. This is the integration by parts formula, and when you want to use it, you have to identify two parts of what you're starting with and choose one part to be the u and one part to be the dv. And like I said last time, the general strategy is to choose the u to be something that you like to take the derivative of, something that gets simpler when you take the derivative, or at least stays the same perhaps. Like polynomial is the classic thing. If you see a x, just like an extra x or an x squared or something like that, that generally is what you want to choose to be the u. And then the dv, you want to pick something which gets better when you take the antiderivative. Let's just do a real quick example. So I don't know, we may have done a similar one like this last time. This is a very simple one. Just to warm it up, just to juice it up. That's what my daughter, it's a quote from my daughter when she was in kindergarten. I thought this was really funny. When we walk to school, right? We get to the crossing, there's a place you got to cross the street. And it's one of those crosswalks where you push the button and then the light changes. And my kid, as many people do, wants to hit the button over and over again until it changes. And I asked her once, like, what are you doing with the button? You really like the button, huh? She said, yeah, you got to juice it up. That was her quote. I thought that was funny. And I still say that about things. So, as a warm-up, as a juice-up, x times sine of x. We got to choose, when you see two things multiplied together in there, that's a tip-off that you might want to use integration by parts. We got to choose the first part and the second part. So we have to choose the u and the dv. And like I said, u, you want something that gets simpler when you take the derivative. dv, you want something that gets simpler when you take the integral, or at least doesn't get more complicated. In this case, I'm going to choose u to be x, because when I take the derivative, it sort of goes away entirely. The du is just dx. And then dv has to be the rest of it, sine x dx. The v is the antiderivative of that, so it's the integral of sine x dx, which is negative cosine x. All right? And so we plug into our integration by parts formula, uv minus integral v du. It is x is u, and then v is negative cosine x, minus integral v, negative cosine x, du is dx. And hopefully in this step you'll know if you're on the right track or not. Hopefully this integral will be easier to do than the one you started with. Does that always just happen like 5 minutes after I start? Didn't that happen last time?
It's like the Dr. Evil countdown.
Yeah. I don't know what that. All right. It's doing fine now. Sometimes yeah, all right. Okay, and yeah, I was saying, at this point you'll be able to tell if you're on the right track, because the integral that you have to do now, you still have to do an integral, but it's simpler than the one we started with. We started with x times sine of x. Now we basically just have cosine. We can take that negative sign out. So let me just simplify a little bit. Negative x times cosine x, and then plus integral cosine x dx. And now we can just do that last integral there. It's easy now. Integral of cosine is sine. I put my plus c. So this is an easy one of the integration by parts. Anybody got any questions about that? All right, we're going to try a couple that are slightly less easy, and then we're going to be able to go on to the next section, I think. So one thing that can happen that is slightly less easy, here's an example. How about integral of 7x squared e to the x? The 7 is not what makes this hard. The 7 is not important at all, really. But anyway, we're going to do the parts. You see things multiplied together inside the integral. This is a tip-off that you might want to do parts. Although multiplication inside the integral sometimes can be handled by a U substitution, but we're talking about parts today. So U and the dV. Any thoughts? What should I choose to be the U? Yeah, let's pick 7x squared as the U. If you want, you could factor the 7 out of the integral at the very beginning, but it doesn't really matter. And then the dV is going to be e to the x dx. I like that. So du now is 14x dx, and v is integral of e to the x, which is e to the x. Right? And so let's plug into the parts formula. uv minus integral v du. I get 7x squared times v is e to the x, okay, minus integral v is e to the x times du is 14x dx. All right, let's just pull the 14 out of there because I like to simplify a little bit at this point. And I'll write x e to the x because I like to write it in that order for some reason. All right, now, here is where things get a little harder than the previous example. Remember I said at this point you should be able to tell if you're on the right track or not, because if you are on the right track, then the integral you end up with here is easier or somehow simpler than the one you started with. Is it simpler than the one we started with? Actually, it looks kind of the same, although instead of x squared, now I have just an x. Is any better? Any butter? Anybody have a suggestion? Yeah. Yeah, how about we do it again? We did integration by parts. You can think of, if you have a polynomial in there, basically the integration by parts will reduce the degree of the polynomial by 1 every time you do it. And so it turned the x squared into an x, and we should be able to just do it again to get rid of the x entirely. So right here, I'm going to do parts again. Sometimes you got to do it more than once, or as I said in the context of L'Hopital's rule, sometimes you squeeze gats till your ellipse is empty. That's a Biggie Smalls line.
Professor, I feel like you love Biggie Smalls, and they just came out with a new documentary on Netflix about it.
Oh, really?
Fantastic. Started last night and through like 2 episodes.
Okay. I actually know very little about Biggie Smalls. I know a bit about like the man. I don't know his music very well. But.
There's another one that's like Who Shot Biggie and Tupac on there. Great show.
Okay, nice. Yeah, I just saw a YouTube video called Biggie. Remember the Tom Hanks movie called Big?
Yeah.
This is a movie where a kid sort of like makes a wish that he was big because he was sick of being a kid, and he turned into Tom Hanks as an adult. And anyway, there's a YouTube video called Biggie featuring a guy who wishes to be Biggie, and he turns into Biggie Smalls. Slightly amusing. All right, anyway, we're going to do parts again. So right here, I'm going to choose my u and dv again. So here I go u something, dv is something. These are different from the original u's and dv's because I'm looking at this integral now. But you want to do the same kind of choice. That is to say, the u should be the polynomial part. So I'm going to choose u equal x, du equals dx. And then dv should be the exponential part. So dv is e to the x dx, which means v is integral e to the x dx, which is e to the x. All right, and so what we end up with is, so this stuff at the beginning I just bring down from before, 7x squared e to the x minus 14 times, and then right in here I'm going to do uv minus integral v du, and it is x, v is e to the x minus integral v e to the x, du is dx. Now we still have an integral to do, but now this integral is very easy and we can just finish it off. So my final answer is 7x squared e to the x minus 14 times x e to the x minus e to the x. And I'll put the plus c at the end. All right, that final e to the x there comes from actually doing the integral one last time. All right, sometimes you got to do it twice. That's the moral of this example. Any questions about that one? Great. I have one sort of especially strange one, and then we can talk about one last thing, and then move on to the next section. So, a strange one. There are other weird things that can happen in integration by parts. Now, this one I'm about to do is especially strange and is not likely to come up very often, but it can happen sometimes. How about, can we try to do integral of e to the x sine x? E to the x times sine of x, all right? We're going to try parts here because they're multiplied, things multiplied together on the inside. Sounds like parts to me. And it turns out actually, the way that I'm about to do this one, you can choose the parts either way around and it won't matter. So let's just choose, I'm going to choose u to be sine x and dv to be e to the x with the dx. You always have to include the dx as part of the dv. In this particular example, like I said, you can choose it the other way around and it'll work out more or less the same way. Well, it will work out the same way eventually. The steps in the middle will look slightly different. What's the du going to be? Cosine, yeah, that's the derivative of sine dx. And then v is integral of e to the x, which is e to the x, right? And so my parts, I go uv minus integral v du. I get sine x, v is e to the x, minus integral v is e to the x, du is cosine x. All right. At this point, you take a look at your situation and you ask yourself, is this actually easier than the integral that I started with? The answer here is not really. I mean, it's not exactly the same, but it's kind of the same. It's not all that different, right? This should concern you a little bit here, but I said this was a strange one. What we're going to do is do the parts again. Even though this one ended up looking more or less the same as what we started with, I'm going to do the parts again. So, parts again. And I'm going to make my choices in a similar way as before. This time I have to use cosine instead of sine. But I'm still going to choose dv to be e to the x dx. What's the du going to be this time? Negative sine x, yeah, and then the, oh, they did it again. And then the v is e to the x. I'm going to try and quit my other stuff I have running here. Sometimes that helps. I don't know. Okay, do the parts here. So we got sine x times e to the x. I like to put the e first. I don't know why. Minus. All right, and then in here, I put the results of my new parts, which is uv minus integral v du. That's going to be cosine x times e to the x minus integral v du shall be e to the x times negative sine x. All right, and just to simplify a little bit, I'm going to distribute minus signs. So this is e to the x sine x minus, I have e to the x cosine x. And then that integral, I believe, ends up having a minus, right? There's a minus sign on the inside, there's a minus sign in front of it, and I'm also distributing a minus sign outside the parentheses, so it's 3 minus signs, which ends up being a minus. Integral e to the x sine x dx. And now, as usual, I look at the integral which remains to do and ask myself, is it any simpler? No, it is not any simpler. In fact, this one actually, I've come all the way back to where we started, right? Now it is actually equal to the integral that we started with, all right? This may seem like bad news that we're just like spinning our wheels here. Just did a bunch of nonsense and ended up with the same thing again. In fact, though, it is not bad news. Check it out. Here's the weirdest part of this example. All of this stuff equals what I started with, right? Integral of e to the x sine x. So that means I can write that here, right? everything I've been writing has been equal all along to what I started with, integral of e to the x sine x dx. And then, check it out, I can take this part and add it onto the other side of this equation, right? I'm going to add integral e to the x sine x dx onto both sides of the equation, and what remains is 2 integral e to the x sine x dx equals e to the x sine x minus e to the x cosine x. And we can divide by 2, and we will have our answer. Isn't that cute? Sort of comes out of nowhere. Now, I should say one very sort of technical thing. Right here, we have to put the plus c. It may concern you. Why wasn't the plus c there before, and where did it come from at this point? Well, we have 2 integrals. Remember, these integrals represent antiderivatives of the function that I'm talking about. And all antiderivatives of the same function, they can differ by a constant. And so when I combine this one and this one by adding this over here, they are not necessarily exactly equal. They might be different by a constant. And that's why when we add this one and combine them over here, this introduces an extra unknown constant in that step. It's a little weird. But anyway, the final answer here is we can now just divide by 2, and we get our answer. 1/2, I'm going to factor it like this. Right? We divide the right side by 2, and I factor the e to the x out. And this is, this is a formula that you're likely to see in any kind of big list of integration formulas of trig functions and exponentials or whatever. That's how we get this formula. You do the integration by parts twice, and then do this weird step at the end. All right? Any thoughts about that? I would describe this as sort of an exotic application of the integration by parts. We are not typically going to do that weird thing at the end. And there is a similar formula involving cosine rather than sine. It's not exactly the same answer, but it's something like this minus sign becomes a plus instead, or something like that. All right. Excellent. One last thing about integration by parts, and it's a simple thing, but I thought we ought to at least do a couple examples. What about definite integrals with the integration by parts? Definite integral meaning it has like the little numbers in the integral sign. I never mentioned how to handle that if you're doing parts. Definite integrals, it's not hard. We just have to talk about how to do it with the parts. The strategy is basically do the indefinite first. Indefinite is like the ones we've been doing with no little numbers. You just put the plus c at the end. Do the indefinite integral first. I'll say all the way, and then plug the numbers at the end. You'll see what I mean. How about, can we do integral from 1 to 3 ln x over x squared? My strategy is I'm just going to ignore the 1 and the 3 until the very end and just plug the 1 and the 3 in at the very end. You'll see what I mean. So let's just ignore the 1 and the 3 for now. How am I going to set this up to do parts? Remember, sometimes you have to rewrite things as products, right? The integration by parts is only used on products, not on quotients like this. Anyone want to suggest how can I rewrite this as a product? Yeah, how about x to the minus 2 ln x, all right? And I'm just going to stop writing the 1 and the 3 for now. We will reintroduce them at the very end. That's the strategy. Great. Now we can do the parts here. Anybody want to suggest what should I choose for the u and the dv? The u should be something that gets easier when you take the derivative. We almost always, if there's a polynomial part, we choose that to be the u. Although actually in this example, that's not going to work. Check it out. Don't write this down because this is not going to work. But if you choose x to the minus 2, that's fine for the u. Then the du becomes negative 2x to the minus 3. This is actually kind of worse than it was before. I mean, the exponent decreased by 1, but it's sort of like further from 0, which is not what you want. And then what's even worse about this is that means you have to put the natural log over here. And then what is integral of ln x dx? I'm telling you, it's not 1 over x, which is kind of what you want to say here. It's the other way around. The derivative of ln x is 1 over x. The integral of ln x has some weird formula to it, which is not what you want. So this actually is not great. The thing with the u didn't get simpler, and the thing with the dv actually gets more complicated. So don't do any of that. Do it the other way around. Basically, if you see ln in there and you want to do parts, you should always choose the ln to be the u, because you definitely don't want to put it in the dv. So I'm going to put u equal ln x here. Then the du is 1 over x dx. The dv must be x to the minus 2, which means the v is integral of x to the minus 2, which is minus 1x to the minus 1, right? These are my parts. And so I go uv minus integral v du. All right. It's going to be uv is ln x is u, v is negative x to the negative 1 minus integral v minus x to the minus 1, whoa, x to the minus 1 times du, 1 over x dx. And now inside this new integral, it looks a little weird, but really they're all just powers of x, so hopefully we can sort of simplify that a bit, and then it should be easy to do that integral. In the front, maybe I'll write it this way, ln x over x. You can write it however you want. And then it looks like plus, if you factor the minus sign out there. What do I get if I simplify the inside of the integral there? This is x to the minus 1. Yeah, 1 over x squared, I believe. This x to the minus 1 is also 1 over x, right? So really we're looking at 1 over x times 1 over x, which is 1 over x squared. Although for the sake of doing the integral, it's a little better to write it this way, x to the minus 2. All right, really I have x to the minus 1 times x to the minus 1, which combines to be x to the minus 2. And then that is a straightforward integral to do. So it's minus ln x over x plus the integral. I increased the power by 1. Actually, it's the same as this this up here, isn't it? I already did the same thing. It's minus x to the minus 1. All right. And now, at the very end, instead of putting plus c as I typically would, now I put the 3 and the 1, right? When you have a definite integral and you intend to do parts, the strategy is just do the whole thing, do every integral there, and then at the very end, you plug your values in. And these values get plugged into everything, this whole thing here, not just the x to the minus 1, but all this whole formula here. You're not allowed to have any x's left over in your answer because the definite integral, the answer should be a number. So I get, when I plug in 3, minus ln 3 over 3 plus negative 3 to the minus 1. And then I subtract and I plug in 1. Minus ln 1 over 1 plus negative 1 to the minus 1. And whatever that is, this is the answer. You can simplify a lot of that by hand, but not all of it, because that ln of 3 won't equal anything nice if you do it by hand. All right, any thoughts about that? Questions? All right, I got one like that for you all to try, and then we can move on to something completely different. So, one for you all is integral from 1 to 2, 1 minus x squared, e to the 2x dx. And I will say something that I mentioned last time here. You should use this integral formula. This comes up often. Everyone knows integral e to the x is e to the x, but if you have an extra constant in the exponent, such as that 2 there, integral of e to the kx is 1 over k e to the kx. You can use that inside one of your steps. All right, I'll give you a few minutes to try that out. And I'm realizing right now I forgot to bring my plug for my laptop, the power cord, and I'm going to run out. So I'm going to go get it, if you don't mind. It's right around the corner. Any questions from the folks back home while we're doing this? All right. You do have to do this one twice. you are going to have to do this one twice.
The b for the second is 1 equal 14 to 2x.
Yeah, you included the 1/2 in there.
Yeah.
So I would. Let's take another minute or so. These are going to take you a little while to do.
So I have a b with b now is negative dx, negative 1 dx. Do I move that to that du, so it's actually technically negative du dx?
No, you don't need to do that. It's just when you use the parts formula, you the integral
Yeah.
and the u part.
So I think that,
That one? Yeah. Great.
doesn't actually matter.
You don't care? Yeah, let's talk about these. I don't know if you're quite finished. This will take you a while, but I hope it's, each individual step is not so difficult. So I began by choosing my u's and dv's in this way. You want to choose the u to be the polynomial part? Almost always that's what you should do. Notable exception is if there's a log in there, that should be the u. But anyway, dv is e to the 2x, so when I do the du's and the dv's, I get this stuff. I hope you got something like that. And then I plug in the parts formula the first time around, gives me this. Now, I decided to simplify the inside of this integral. As I was looking at, some folks just sort of left things in this way, but which is fine. You'll end up with the same answer eventually. Simplifying the inside of the integral, these 1/2 and the 2 will cancel. And also I pulled the negative sign out, so it ends up being plus, and then this business. And how do you do the integral x times e to the 2x? You do parts again. So I choose the x to be the u, e to the 2x to be the dv. Do this, I end up with this, and that's where I stopped. I'm not done yet, but I just didn't write the rest of it. So this is 1/2 x e to the x, and then finally I do the integral here, pull the 1/2 out, do the integral of e to the 2x, I get yet another 1/2. So this is another 1/2 e to the 2x. This is the integral, the antiderivative. I hope you got something like that. If you didn't simplify in the same way I did in the middle, your answer might look slightly different, but it should be the same. I mean, it should be equal eventually. Any questions so far? This is not quite the end, but this is almost the end. And now I'm going to plug the values. The values were, what were they? 1 and 2? Yes, 1 and 2. So I go 1 and 2. Sorry, I wrote e to the x there in the middle. It should be e to the 2x. These are all e to the 2x's. Sorry about that. All right, and I plug in the 2, and then I plug in the 1. So I get, plugging in the 2, 1/2, 1 minus 2 squared e to the 2x, 2 times 2, plus 1/2 times 2 times e to the 2 times 2 minus, this is 1/2 times 1/2 times e to the 2 times 2. All of that is what you get when you plug in 2. Then minus all of this, plugging in 1. So 1/2, 1 minus 1 squared e to the 2 times 1 plus 1/2 times 1 e to the 2 times 1 minus 1/2, 1/2 e to the 2 times 1. And as usual, you could simplify a lot of that by hand, and I don't care. All right. Any questions about that? I hope you got something that looked something like that. Any questions from the folks back home? I always care for the folks back home. I hope you feel that. All right. Excellent. I think this is all that needs to be said about integration by parts. Sometimes, like this example, will take you several minutes to work it through, but I hope that it made sense. All right. Great. This was in the book, section 7.1. Chapter 7 is all about sort of more and more tricks for doing various different kinds of integrals. And the two sort of foundational tricks are the U substitution and the integration by parts. And we're going to use them in different contexts to do sort of more and more types of integrals. And I think we're ready for the next section. Is called Trigonometric Integrals. So this in the book is section 7.2. Trigonometric Integrals. This is about integrating powers of sines and cosines. For example, this is like integral of one we're going to do in a few minutes. Sine squared x cosine to the 5th x dx. Something like that. This is what the book calls a trigonometric integral. They're always going to be some power of sine times some other power of cosine. Is that hard to read? It says sine squared of x cosine to the 5th of x dx. All right? How can we do this? Well, thus far, our only two tricks are U substitution and integration by parts, right? Let me just say the parts is not really going to work as written. You know, it's natural to say, okay, maybe I'll make this my first part and this my second part, right? So one of those, choose one of those to be the U and the other one to be the dv. It's not going to work so well. Whichever one you choose to be the dv, the U is not so bad. You can take the derivative of one of those things. Like if you choose one of those to be the U, you will be able to figure out what the du is. But the v is going to be a problem. If I do, say v equals sine squared x, sorry, dv is going to be a problem. If I take the dv to be sine squared x dx, then the v will be integral sine squared x. Anybody know the formula for that? The answer is no. I mean, there isn't really a nice formula for that. Like, there is a formula. It is known to mankind, but this is not a nice integral to do. So Huh? This is going to get more complicated than it is in any case. So this is a bad choice for the integration by parts. But if you choose it the other way around, it's not going to be any better. You choose cosine to the fifth to be the dv. This is also going to be a bad choice. So all of this to say, parts won't work. The methods that we're going to use are tricks which are based on weird U substitutions. They're going to look weird the first time you see them, although, you know, it's once you do a few examples, see some patterns, it's not so weird. Parts won't work. We're going to use U substitutions and some trig formulas. Now, I often say, I don't care if you have memorized the more obscure trig formulas. The one which is most useful in these is this one. So you should know this one. Everybody, I've always said you should always know this one. Also, there's a more obscure one that we are sometimes going to use in this section, and it's this. Sine squared of x is 1/2 1 minus cosine of 2x. This comes from the double angle formula or the half angle formulas, which you've probably seen before but don't have memorized. That's my position in life. I know that these formulas exist. I don't typically have them memorized when I'm just minding my own business. And there's a similar one for cosine. So write these down somewhere. We will use them in this section. I still will not expect you to have these formulas memorized at all times, but when you're doing the homework problems for these, you will want them. And on our tests or on our quizzes, I will give you these formulas. Not the first one. Sine squared plus cosine squared is one. Everybody knows that. Okay. Anyway, what's the point of these formulas? Sorry. Also, I'm just going to tell you all the ones we're going to use. These are simple, but this is just like integral of e to the kx is 1 over k e to the kx. What about sine and cosine if you have an extra constant inside? It looks like this. Integral of cosine is 1 over k sine of kx. Let's see. If you have an extra constant on the inside when you do these integrals, the result is dividing by that constant on the inside. This is because if you have a constant on the inside and you took the derivative, you would have to multiply by that constant by the chain rule. If you take the antiderivative, it ends up you have to divide by that constant. Not a big deal. All right. So put these in a list of in a box somewhere. These are all the random formulas that we're going to be using in this section. The first one really is the most useful, even in this section. We're usually going to be able to get by just using that first one, and when we're not often going to need the other ones, which is good news. All right, let's try a simple example. You know, I said we'll come back to this one that I wrote first, sine squared times cosine to the fifth. That one is actually a little tricky. Let's start off small. So simple example would be something like cosine cubed of x dx. All right. Of course, it really means this, cosine of x cubed, right? That's what cosine cubed of x means. And like I said, we are going to, all the tricks in this section are based on U substitution. So we are going to do a U substitution, although the obvious choice, you know, the standard U substitution is you choose something which is the inside of the parentheses or something like that. So in this example, the obvious choice would be, or I'll say the typical choice, which is not going to work, but the typical choice here is U equals cosine x, because it's on the inside of the parentheses or whatever, and that's usually how we choose the U. It would be U equals cosine x, which means du is sine of x dx. But this is a problem because when we do the U substitution, it involves looking here. You have to look for where the U is, if I were to try to do this U substitution, this would become integral of U cubed dx. But then, how am I going to turn the dx into the du? It's not going to work because I don't see any sine of x in here to combine with the dx and make the du. This is part of what it requires to do a successful U substitution. Any extra stuff in the du has to already be present inside the integral sign. So here, we can't finish the substitution because, really, it's because there's no sine of x in there, which we require in order to plug in the du. We're missing this sine x, which is necessary in order to finish the U substitution. All right? So, instead of that, here's the strategy. So, don't do this U substitution. It's not going to work. Instead, this is sort of my slogan. The name for this strategy is save one. I'll tell you what I mean by that. What we're going to do is save one of the cosine x's and then turn the others into sine. And what I mean by that, this is hard to read. I'll write that again. Turn the others into sine of x. What I mean by that is, we begin with, cosine cubed of x. I'm going to split it up into cosine squared of x times another cosine of x. That's the one I'm saving over on the right there, cosine x dx. I saved one of them. The rest, there's two others, cosine squared in the front. I'm going to turn it into sine of x according to everybody's favorite formula, sine squared plus cosine squared equals 1. This cosine squared I'm going to write as 1 minus sine squared of x. And now, this looks more complicated, but actually it's better because now we can do the U substitution, and we do have the extra thing sitting there that we need in order for the substitution to work. So now we do the U substitution. This time, actually, I'm going to use sine of x, and then du is cosine of x dx. And this time, since I saved that one cosine, it becomes the du. So when I do this substitution, it says 1 minus u squared inside the parentheses times du. And now this is great. Now this is just a very simple integral. It's just a polynomial, right? So this is a somewhat, it's not, I was going to say it's an elaborate U substitution. It's not really that elaborate. It's just a tricky little trick to save one of the cosines and then turn everything else into sines. That's the trick. All right. Anyway, let's just finish it off. What do I do for integral of 1 minus u squared? Well, it becomes u minus 1/3 u cubed, right? It's just a polynomial at this point. And I put the plus c there. And then the last step in a U substitution is to replace the u with whatever it was in terms of x. So my final answer is sine x minus 1/3 sine cubed x. That's it. So the slogan here is save one of them to become the du, and then rewrite all the other ones.
Why is it sine x minus 1/3 sine x? Wait, where is that second?
Yeah, I replaced u with sine x, so u cubed became sine cubed of x. Right? Let's try another one. So actually, at this point, we are ready to try that one that I wrote at the very beginning. Any questions about this one, first of all? This is a little weird, but I think once you get used to it, it's not so tricky. How about integral of sine squared x cosine to the 5x dx? All right. So let me try and say in words, actually, before we do this example. in words. Can I do this? Nope. I thought that was going to work. Sorry. The basic trick here is, this is the save one trick. Save one cosine x, and then write everything else in terms of sine x. Or you can do it the other way around. It depends on what you see inside the integral. Maybe you want to save one sine x and write everything else in terms of cosine x, and then do the similar thing. So I'll say, or save one sine x, and then write everything else in terms of cosine x, all right? So you have to decide for yourself which way you're going to do it. Do I want to write it all in terms of cosines or write it all in terms of sines? And which one am I going to save one of? Hey, let's just try another example. Sine squared x cosine to the 5x dx, all right? Now, how do I decide which one to save one of and turn everything else into the other thing? It amounts to looking at evens versus odds powers, because remember, we're rewriting everything in terms of squares. And so if you save, like in this example, I'm going to save one of the cosines, and the rest of it is cosine to the 4. And then that I can write in terms of sine squared somehow, because cosine to the 4 involves cosine squared and then squared. Whereas if I save one of the sines, then I have one extra sine left over, and that cannot be written in terms of cosine squareds, because it's only one sine. So here, we're going to basically save the one with the odd power. Now, if both powers are even, you have to do something a little fancier, but we're not there yet. Save the one with the odd power. So I'm going to write this as integral sine squared x times cosine 4x times cosine x dx. And that cosine x dx at the end will become the du in my substitution. And we're going to try to write everything else in terms of sines. So I have to rewrite these. Save one cosine and then write these in terms of sine. What am I going to do with cosine to the 4? We know how to handle cosine squared. You write as 1 minus sine squared.
Yeah, 1 minus sine squared squared.
Yeah, right. Cosine to the 4 you think of as cosine squared of x squared, like that. And then cosine x dx. And so this becomes integral sine squared x, and then this is 1 minus sine squared x squared cosine x dx. So I wrote everything else in terms of sine squareds. And now we can do our U substitution. I say U is sine x, du is cosine x dx. And this, when I write in terms of u's, just becomes u squared out here, 1 minus u squared squared du. Now this is a weird looking integral, but actually it's not so hard to do. Anybody know how to do an integral like this? It looks strange. Any folks back home can shout it out if you got an idea. Yeah, how about you just, I mean, this basically is a polynomial. It's written in a weird form, but you should be able to rewrite this like in the standard way as a polynomial. What you got to do is like the FOIL thing right here, right? You square out this part. So I'm just going to simplify this so that or expand this so that it looks like an ordinary polynomial. When I square that out, 1 minus u squared, this becomes 1 minus 2u squared plus u to the 4, right? What I just did was 1 minus u squared times 1 minus u squared. And you get, well, you get what I just wrote there. 1 minus 2u squared plus u to the 4, right? And then we can distribute the u squared, and we'll have a very ordinary looking polynomial, which we can take the integral of. So I get u squared minus 2u to the 4 plus, what's the last one going to be? U squared times u to the 4? Your choices are 8 or 6. It's 6. Yeah, when you have two different powers of the same thing, you add the exponents. So it is u to the 6. The time when you multiply the exponents is when you have an exponent inside of another exponent, then you multiply. All right, great. Now we can finally do the antiderivative. We get 1/3 u cubed minus 2/5 u to the 5 plus 1/6 u to the 6 plus c. And we plug everything in. 1/3 u is sine x, remember? So this is 1/3 sine cubed x minus. Yes, thank you. I forgot to actually change the numbers. 1/7 u to the 7th. Okay, so 2/5 sine to the 5th x plus 1/7 sine to the 7th x plus c. All right, that's it. It's that simple, right? This is the kind of thing I look at and I think, man, whoever came up with this is a crazy set of tricks. But really, it's all just kind of simple tricks. There's no real, big, hard idea here, in my opinion. It's just some especially cute decision making about where exactly you're going to rewrite things and do your U substitution. Anybody got any questions about that? This is called Trigonometric Integrals. I would like to do, we only got like 15 minutes left. What I said before is, and I'll write it down. So this basic trick works when we have one power is odd. I mean, when we have sines times cosines, where one or the other power in there is an odd number. So if you have something like sine to the nx times cosine to the mx, if n is odd, then you save 1 sine x. If m is odd, you save 1 cosine x. If neither of them is odd, then you have to use a different strategy. But maybe we'll leave that till next time. I had an example that I wanted you guys to try of a similar type of what we just did. Let's try integral sine cubed x cosine cubed x dx. I want to see what you all think. Now, in this case, they're both odd. That means you can choose either way around. You can choose to save one of the sines and write everything else in terms of cosines, or save one of the cosines and write everything else in terms of sines. Maybe just for the sake of us all getting the same answer. If you do it slightly differently, your answer will look differently. They will be equivalent, but they'll all look different. I will just suggest, let's save one of the sines and then write everything else in terms of cosines. See if you can make it happen. You should be able to follow fairly similar to the example that we just did. It may take a few minutes, but we got a few minutes. Yeah, try it out. I think you will find it works okay. In that case, you do want to move the minus sign to the other side. The thing you always wanted to do in the parts, but you shouldn't. In the U substitution, you should. All right, let's talk about this. I think most people work this out. So if you follow my suggestion, which is save one of the signs, then what I mean by that is write it this way. So in this sine cubed, break out one of the sine x's from there. What remains will be sine squared, and of course all the cosines, cosine cubed x. You could instead save one of the cosines, and it would work out just the same way. So this was just a suggestion so that we would all do the same process. If you do it using cosines, then it would be slightly different. Anyway, I break out one of the signs. What remains is sine squared of x, which I write as 1 minus cosine squared of x. And now I can do my substitution. U equal cosine x. The du is negative sine of x, and because I'm doing a U substitution, I do want to move this minus sign out to the other side so that when I see sine x dx, that's minus du. So to do the substitution, it becomes u cubed 1 minus u squared times negative du. And this minus sign will just sort of, I mean, you can factor it all the way out of the integral if you want. I guess that's what I'll do. Minus, and then I'm going to distribute in here, u cubed minus u to the 5 du. I hope this is what everybody got. Any questions so far about that? Great. And then, now you just do, this is polynomial integral, so I go minus, and then it's 1/4 u to the 4. Minus 1/6 u to the 6, and plus c. There's no values to plug in. Of course, you can do all these same tricks if you do have a definite integral. Then you just plug the values in instead of doing the plus c at the end. And finally, I replace the u's with cosines. So this becomes minus 1/4 cosine to the 4 of x minus 1/6 cosine to the 6 of x. Like so. And that's the answer. Anybody got any questions about that? Now, if you had done it the other way around, where you saved one of the signs and made the u equal sine of x, your answer actually would look totally different because it wouldn't have cosines in it, it would have sines in it. It would not be very easy to verify this, but your answer would be equivalent to this one. Just in order to show that they're the same, you'd have to use some weird trig formulas to reconvert all the sine squares into cosine squares or whatever. I didn't want to get into that. All right. Any questions about that one? Great. Okay, we got 7 minutes or so left. I think that's enough to just do a little intro to what about when both powers are even, all right? This trick that we've described here of the save one of whatever, that works when one of the powers is odd. What if they are both even? In that case, we got to use those other weird formulas. So these ones that we've done so far do not involve those other weird formulas. I will refresh your memory. The other weird formulas were this. Sine squared x is 1/2 1 minus cosine of 2x. A similar one for cosine. Cosine squared x is 1/2 1 plus sine of 2x. Ooh, that one's, all right. It lasted longer that time. I got the little pinwheel on my computer at the same time. Something weird's going on. My computer has seen better days, I'll tell you that. I keep telling them to give me a new one, but they're being stingy with their computers. Yeah, I mean, I don't actually own it, you know, but I act like I own it. I take it home with me every night. I tuck it into bed. I play my video games on it. I don't really because it's too old. But okay, anyway, these formulas, what's the point of these formulas? You use these when when all of the exponents are even. Let's just do a very simple example, and then we'll talk more in depth about this next time. What if it was just integral of sine squared of x? This is just sort of a proof of concept. This one is very easy, but to impress on you why those two formulas might be useful for anything. In this case, we can just immediately use the top formula there. Sine squared of x is 1 minus cosine of 2x. 1/2 of, so I'm just going to plug it in. 1/2 of 1 minus cosine of 2x dx. Basically, what these formulas mean is sort of on a very informal level, we can convert two sines into a cosine. Right? Here I started with sine squared. There's two of them, which means if I try to save one, it's not going to work properly. But it is a fact, using those two formulas, you can convert a sine squared into a single instance of cosine. And then actually, this does not require a U substitution at all. So over here, I can factor the 1/2 out. And what remains is 1 minus cosine of 2x. And I can just do the integral there directly, right? The integral of 1 is x. I got 1/2 on the outside. The integral of 1 is x minus, what is the integral of cosine of 2x? This is what I mentioned before. The integral of cosine kx is 1 over k sine kx. And so the integral of cosine 2x is 1 over 2 cosine 2x. That's right. There's no need in this case, because all I had was just a single even power of sine of x.
Yeah, in your formula on the right side, you
Oh, yeah, I used the formula incorrectly. Sorry. This should be a sine here. That's what you meant. Thank you. The integral of cosine is sine, so you better do that. All right. So this is where these other two formulas come into play. If for some reason you have an even number of everything, remember we really want to have odd numbers. You can reduce one of them sort of by one by exchanging an even number of sines for just or you exchange two sines for one cosine, and this allows you to get around the bad situations in which you don't have enough or you have too many of something or other. All right, so we'll do a few more examples of this even case next time. I think that's good enough for today. Yes, you will see a new homework assignment. It's not there yet, but sometime today you will find it. Due on Wednesday as usual, and we'll be back to our normal quizzes on Friday schedule. Yes, that's what I